Welcome everyone. We represent data infrastructure at Meta, supporting varied set of use cases for analytics and machine learning across diverse personas. Today we're going to talk about ML monitoring and observability. Before we get into the presentation, let's introduce ourselves. My name is Animesh Dalakoti. I'm a product manager supporting ML monitoring and observability.
I'm Partha Kanuparthy. I'm a software engineer in the data infrastructure organization at Meta, and I primarily focus on building scalable platforms for ML monitoring and observability.
I'm Kunal. I'm a software engineer on Dev Infra, and I primarily spend my time working on tools for machine learning engineers.
So let me quickly walk through the agenda today. We have taken a particular class of ML problem called any explosion, which we're going to explain towards later part of the presentation. We're going to assess a storyline from what exists today in terms of how we troubleshoot and debug it versus how our future looks like from ML monitoring platform perspective. We're also going to talk about a product story end to end towards the later part of the presentation. We have picked, although a particular class of problem, but what we talk about today is agnostic to that problem and applies to the overall machine learning ecosystem. So before we go into the next step, let's look at how Meta leverages machine learning today. So from Meta perspective, we have a bunch of use cases and product surfaces where we leverage machine learning. From recommending an interesting reel to our end user, to personalizing ads, to building the metaverse using AR/VR, as well as for efficiency while running some of the largest warehouses in the world. All of these machine learning use cases are driving significant amount of data and also driving the complexity of the ecosystem. As we can see here, there has been tremendous growth in the training dataset size, as well as in terms of the ingestion bandwidth from 2x to 4x for these use cases. As well as the model complexity size has been increasing tremendously historically in terms of the compute size that we require. Now let us look at what is a simplified version of end-to-end data flow at Meta. The journey of data starts from apps that we own today, and then it flows through the logging and ingestion pipelines and ETL, driven by batch and streaming ecosystems, and eventually landing into the warehouse. From here, we have our feature frameworks that generate these features. We get label data from internally and externally in the ecosystem, and then we leverage this to generate our models. These models are then served for inference time. Current state of ML monitoring is siloed, and we are looking at how we build an end-to-end ecosystem around this. So let's look at what are some of the challenges today in terms of this ecosystem. There are some common issues that we see. Loss explosions or any explosion that we're going to talk about in depth today is one of the class of problems. There are feature quality issues such as coverage, distribution, freshness. There could be throughput drops. Then there are other classes of challenges, which includes the size and complexity that I talked about, as well as in terms of features models, but also in the number of teams that are involved in case a step happens across this journey of data. There's a lot of fragmentation and tech debt that exists today. All of this results in increased time to debug and troubleshoot these classes of problems, resulting in impacting the top line metrics, causing developer productivity loss, as well as wastage in training resources. So next, I'm going to hand it over to Kunal, who is going to talk about the any explosion problem, provide us an overview of the problem itself, current pain points that exist in troubleshooting and debugging it.
Thanks, Animesh. And now I'll take you through an example of a problem I've seen a lot of ML engineers tackle over the past couple of years: any explosions. First, let's describe what an any explosion is. Any stands for normalized entropy. It's how we measure our model's performance. And for the sake of this talk, I'll just say that lower is better. And any explosion is when the value goes up really high, and we can't really explain what went wrong and why that happened. We've diagnosed any explosions to really different root causes. Everything from issues with model design, corrupted features, sometimes it's even been bad hardware. And it's really painful to figure these out. The biggest problem with an any explosion is that there is no stack trace. The way I see people tackle these is that they'll assemble a virtual team of experts from every single layer of the training stack. There'll be someone from the root infrastructure, someone who understands the data, someone who understands the model, and someone who's just looking at the hardware itself. Then they'll build out a massive table of different runs that they're testing out, and they'll try out different hypotheses, and they'll A/B test their way to a solution. Along the way, they'll build a lot of Jupyter notebooks and try to dig into what was going on. This is really painful, happens frequently, and eats up a lot of time. When you try to debug something like this, you generally have three areas to dig into. The problem could be inside the model itself, the problem could be with data, the problem could be with the platform that you're using for training. And of course, you're always blindsided at times because the training stack is massive and there are so many things that can be going wrong. While I won't talk through every single one of these, I will give you some concrete examples of things I've seen happen for any explosions and some of the automation we've been building or thinking about building to make it easier to work with them. First, one of the most common examples for any explosions or one of the most common causes for any explosions that I've seen is bad upstream data. Sometimes you get too many NaN values and some dates are corrupted in the model. And the way people deal with these is to basically try and block out that data and retrain the model with data surrounding those dates. Other times, they'll try to manually profile the data and look for any anomalous values. We can make this much, much easier for people. We can figure out if there was any anomalous data and alert them upfront before they start training. We can try to root cause feature issues to upstream data to make sure it doesn't happen again. We can also try to do some correlation. So if the model is misbehaving, see which features changed around that time in a similar way, and try to identify and pull them out, then highlight them for the users. To be able to do this, we need really clear lineage from the platform. It needs to be able to tell us which features a model is using, where the data is coming from, how it was transformed. And to be able to fix it automatically for users, we need to be able to programmatically modify the model and change the data around. Another cause for any explosions that I've seen frequently is simply a too high learning rate or bad hyperparameters. The way people seem to work around this is to rely on some model experts who are really familiar with that architecture, and they'll give them best case examples for values. They'll be like, oh, 0.03 is too high, you should have used 0.02 instead. And then people will simply manually tweak these values lower and hope for the best. We can help people in this case by simply looking at the set of hyperparameters that are used in similar models and then warn them if they're using something anomalous. We can also apply a predefined config to their model and say that this should help fix it and retrain the model with the hyperparameters in case we notice any explosion. Automation means that we should be able to access these hyperparameters pretty easily, and we should be able to apply them to the model as well, which is kind of important. More examples of any explosion causes include the model itself. Sometimes the architecture is bad and could do with clipping. If you search for gradient explosions on Stack Overflow, that's actually the first answer. And the way you figure out where to apply clipping is to look at which values in the model went too high. And for that, people end up using TensorBoard, adding a lot of logging manually. Sometimes they even have to rely on standard error, or they'll look at and explore the checkpoints of a model. We should be able to make this much, much smoother for them. In some cases, after any explosion, we'll add logging ourselves and retrain the model, so by the time the engineer comes and looks at the data, we already have really rich data for them to analyze and can point them right to where they could apply clipping instead. We can also simply track how values are changing across checkpoints to figure out what's going wrong and give people a hint about what to do. I'm sounding like a broken record here, but you really need to be able to programmatically change the model and add logging. And to make this easier, we really also need to be able to look inside models and find any values we need inside them by using logging or analyzing checkpoints or whatever way is possible. Then, of course, sometimes just the code goes wrong and you have bugs that manifest as any explosions. The training platform can be broken and some bugs can manifest as the spikes in parameters. Sometimes it's simply synchronization issues. Sometimes it's broken hardware. We can help people out by bisecting different versions of the platform and figuring out if training actually works properly with older versions and then root causing the problem that way. The standard SRE stuff also applies, just monitoring your systems, monitoring the hardware for its behavior, and alerting users if the infrastructure is misbehaving helps smoothen out a lot of issues too. One of the other platform requirements for this is that we should make it really easy for people to be able to look at the training logs across all the distributed systems available. And with that, I'll hand over to Partha, who's going to walk you through the platforms we've been building to help with these kinds of problems.
Thanks, Kunal. In the next section of the talk, we'll be covering the ML monitoring and observability story in terms of the platforms behind it and the product story around it. So I'll be talking about the platforms, and Animesh will cover the product side. Let's take a step back and look at the big picture. And this is something that we have already seen in the previous section of the talk. A typical triaging and debugging workflow starts with a top line anomaly, a change in a top line metric. And there are really three different classes of problems or root causes that are being solved by ML engineers, scientists, and data engineers and infra engineers. There are problems related to models, there are problems related to data and features, and there are platforms issues that can in turn impact model and data properties. And then there are unknown unknowns. And the goal for building a platform is also to enable at least understanding a little bit of the unknown unknowns, enabling enough support for adding instrumentation to cover unknown root causes as they show up. So before I start talking about platforms, I'll talk about a few design principles that we have uncovered and that we follow as we are building out these platforms. In the last couple of years, by looking at triaging and debugging workflows undertaken by ML engineers, scientists, infra engineers, while they are going through their operations and their model authoring and data authoring experiences. The first of them is support for debugging and automation. These are really, they come in the form of simple abstractions that we can provide. And we discovered there are two kinds of abstractions that will really simplify the life of someone who is trying to improve their operations and their experience working with models day to day and data and features day to day. The first is enabling abstractions for end to end analysis. In operations, typically a top line impact goes into the model debugging, goes into feature debugging, goes into training debugging, and walks back all the way into raw data if the root cause went back as far as the raw data, for example, corruption. So, providing abstractions that support this end to end debugging and providing abstractions for automating workflows for end to end debugging at low latency in near real time is a significant, interesting principle. The second is supporting cross layer analysis. These are not end to end, but within a single stack. Typically, machine learning systems are multi tenant and highly distributed large monolithic systems, for example, the training stacks. And supporting cross layer analysis that take a particular job, such as a training job, and dig all the way from the distributed systems layer into the GPU and tie all of these together and do analysis of why a job did what it did is very significant abstraction. The second is abstractions that we don't want to expose, such as details of the training platform, details of the data and model versions instead of point in time analysis support, details of the checkpoint formats across multiple training platforms or frameworks, details of the data format, details of the tables, and the physical layout is something that we don't want to expose. The next is enabling support for fine grained instrumentation, such as instrumentation that enables causal analysis, instrumentation and metadata that encodes causality in distributed execution across multiple events, such as training, and inference across a partitioned set of models. What we have realized as the next design principle, what we have realized is that debugging and triaging experiences, especially in the case of a large operational issue, typically involve a common set of computation and I/O that is common across multiple parallel debugging workflows. And this is what we are calling common sub-expressions. A typical example is that of checkpoint analysis on a model that had an any explosion issue. And enabling multiple analysis on that checkpoint involves common sub-expressions such as I/O on subsets of the checkpoint and transformations and deserialization of that subset. Cross-layer analysis, especially across lower layers of the stack, is another common sub-expression. Finally, enabling on-demand instrumentation for cases where there is an anomaly or an operational issue and there needs to be additional fine-grained instrumentation. So I look at two sets of platforms, and my goal is to cover high-level goals in building these platforms and some of the associated challenges. There are platforms that we are working on for model debugging, and there are platforms that we're working on for feature and data debugging. So let's look at model debugging in the first place. Model debugging is a very complex undertaking because models are large, they're growing in size. The number of features that are input to the models are also very large and growing year over year. So, instrumentation of the model, and especially fine grained instrumentation that enables analysis at every layer, for example, of a deep learning network or every subset or contiguous subset of neurons in a deep learning model during training and during online training during inference is complex. Enabling supporting this at low overhead is a significant goal and challenge as well. The second is that of enabling low latency abstractions for analyzing this data. For example, model checkpoint analysis. Both checkpointing itself of a very large model and analysis of a checkpoint is a complex undertaking. And as I mentioned, enabling common sub-expressions, discovering them and supporting them will improve time to do the checkpoint analysis itself. Instrumentation of very large models can be intensive, and instrumentation in the presence of handoffs between CPU and hardware acceleration such as GPU is going to have significant observer effect and performance impact. Capturing domain knowledge from model authors and from teams that are working on the model and enabling abstractions to capture these is one of the challenges in itself because it is complex and it changes very fast over time. And finally, support for hyperparameter debugging and root causing down to hyperparameters and model parameters requires support for additional frameworks and compute capacity, such as support for A/B simulations. So the other side of the platform support for monitoring and observability is in the context of feature debugging. And this enables support for feature debugging of not just feature problems such as feature distribution changes, feature coverage issues, feature corruption, but it also enables root causing all the way upstream into the data source or multiple data sources back to the raw data. Feature debugging typically starts from a model anomaly that ties into one or more features and enables upstream debuggability and root cause analysis. As we all know, there are two kinds of primitives that are required for enabling end-to-end debugging all the way down from feature back to the raw data sources. The first is that of lineage. Lineage tracks the transformations or sets of transformations that eventually lead to a feature materialization starting from all the raw data sources. And capturing this lineage is a challenge. The second is that of capturing properties of all the data sets, of features, of labels, and for every node in the lineage tree of features and labels. And the third is enabling understanding impact to the features and labels as a function of the pipeline reliability issues. For example, a pipeline that leads to stale features, a pipeline that leads to downtime in certain data availability, and finally, enabling end-to-end analysis that includes the metadata as well. Some of the challenges are lineage. Lineage is pretty dynamic. It can change when, for example, you update a code that is related to a data transformation for a feature computation, or it can actually be a property of an if condition that is used in a feature computation. Statistics computation can be resource intensive, and depending on the size of the table in metascale, we are talking about very large table sizes that require a lot of additional resources for computing statistics over and above the feature computation itself. Problems such as any explosion require fine-grained instrumentation, such as ordering of the data samples that arrive at a model while it is being trained. And it is hard to record fine-grained instrumentation at scale. And finally, the growing size of models and the associated features in the models makes it hard to not just do instrumentation, but also do needle in a haystack analysis and reproducibility. So we looked at platform support, goals and challenges for model debugging and for data feature and label debugging. Let's look at under the hood what it takes to build the platforms that enable support for all of these debugging experiences and data. This is what we call the monitoring and observability platform. There are really four requirements here. One of them is to enable low overhead, but at the same time, fine grained instrumentation. The second is to enable support for causal analysis. That is really the key to enabling end to end bottleneck analysis. For example, for debugging a training job or stitching that into the model layer to debug the impact on model accuracy and convergence. The goal behind this is to enable metadata instrumentation and capture at low overhead. Third is to enable query support for interactive latency queries with multidimensional filters because these are very sparse number of dimensions on the telemetry and on the statistics and on the lineage. And finally, putting all of this data and metadata together in a centralized platform to enable low latency, near real time analysis for debugging and triaging. So taking a look at the high-level picture of the platforms that compose our end-to-end ML monitoring and observability, the top part of the diagram shows the canonical high-level ML workflow that starts from raw data through the transformations, ends up in features that end in a model during training or a model in serving. The first investment that we made was in statistics platform that captures both lightweight statistics in the critical path of a data transformation job and heavy duty complex statistics asynchronously but in near real time. The second is traceability that enables lineage of the dataset from raw data sources to features across all of the features at scale. And a storage and query platform that centralizes all of this statistics lineage and all of the systems telemetry and model telemetry and metadata at a single place. And finally, enabling authoring experiences and debugging automation and triaging automation using a near real time set of low latency abstractions on all of this data. So that's about the platforms. Next, I'll hand off to Animesh to talk about the product story behind ML monitoring and observability at Metascale.
Thank you, Partha, for walking us through the ML monitoring and observability platform. Next, let me talk about a little bit about the ML monitoring stack. At Meta, there are different product verticals in different level of maturity, different classes of requirements, and therefore the way we envision this platform is represented here. At the bottom of it is a platform component, which Partha already described. Then there are ML abstractions, which provide efficient abstractions for running faster analysis. Then there are some of the domain-specific solution platform for authoring for analysis. And then there are product surfaces which span end-to-end, providing visibility into the ecosystem that I earlier talked about within Meta. Next, let's look at a product story that I initially mentioned about how we are envisioning debugging the any use cases with this platform. So some of the users that we are personas that we plan to support are the ML end users, ML infrastructure users, platform engineers, and imagine how this journey would look like. So first of all, there's an authoring ecosystem where users can configure and write these detectors with minimal code using the debugging platform. Then our model anomaly detection detects these any explosion problems in real time based on the training stack logs that we collect. Then we have analyzers that use these logs and feature stats as well as attributes and then attributes this problem to a small set of features. Further upstream, we're going to take those particular features and do upstream analysis using the lineage, using the statistics, reliability data, as well as events to isolate it to a particular, let's say, a node within this end-to-end journey of data. Then within the particular node, we're going to leverage existing tooling for that specific pipeline ecosystem to further troubleshoot and identify the true root cause of the problem. And at the end of this, what do we get? We get a reduced MTD and MTDR, insurance of the top line metrics, predictability, as well as improved developer productivity. So that's what we have today for ML monitoring and observability. Hope you enjoyed this session, and we would love to get involved via these channels. Thank you so much.